Empty, don't tempt me.
T.H.O.D. man, here I am, I'll be damned if it ain't some shit. Time to spread the bud, the lyrics over harmony grit. It's the mood killer death trap. Yes, I'm a jet black ninja. Coming where you rest at, surrender. Step inside the ring, use the #1 contender. Looking cold.
So, here on this slide, I'm just going to list a couple theorems that showed up in your book. They might or might not be pretty useful. So I'll just list them here, but we won't do any examples because they're good to know, but they're pretty simple. So what this one says is the double integral over d of f of xy plus g of xy dA equals, and this is just going to be split up basically. So this is double integral of f of xy plus double integral over d of g of xy dA. So that's what that theorem says, is that these two sides are equal. Okay, so you can basically just split up the functions inside. And the second theorem is that if you have something like this, where you have double integral over d of c dA, where c is a constant, so where c is a constant, so constant being not a variable and staying constant basically, which just means like a number, like 2 or 3 or whatever. Okay, so when that happens, then you can always just bring c outside, because as far as constants go, they're pretty neat because you can just move them anywhere and they won't really do anything. So we could just move it out in front here. So it'll be c times integral over d of 1 dA, or of whatever else is in there. Okay? And also, this can be written as c times area of d. Okay? And I'll explain why this goes to this in this step. Alright? Okay, next slide. So, the reason why this 1 dA turns into area of d is because if we look at it, then let's see. So what I said in the beginning was that double integrals give us volume, right? That's what we're measuring with the double integral. So let's look at it. If we have 1 here, that means that that's in the place of our f of x comma y, right? So that just means that f of x comma y equals 1, okay? And what this means, this determines z at any given point. So that means our z value is 1 at all points, basically. So that is going to give us a plane. All right, so z, no matter what x and y are, they could be doing whatever they want down here, but z is going to be a constant at 1. All right, so it's going to go, yeah. So this plane is just going through z equals 1. Yeah, so then basically, let's say you have any domain down here. It doesn't even have to be a rectangle, just anything like a blob, okay? So here's our domain D lying on xy, okay? And then whatever, when you draw vertical lines up, right? And then until it touches the magic carpet here. So in this case, the magic carpet, or whatever, the flying carpet is flat. It's parallel with the floor, and it's at 1. So if we think about it, when we have the signed volume here, that's going to be d, whatever that is. If we think about like geometrically, right? So let's say this is like a cylinder or something. Let's say we actually had something more like a circle. Okay, so circle here, and then here's our plane at 1. It's crossing at 1. Here's our z, y, and x. Okay. So here is our volume. Okay, so this is the kind of the solid created. So this is d down here. Okay, and here's our height, right? And so to get the volume of the cylinder, you would do the surface area of the bottom. So that would be d times your height. Okay, so this is area of d, surface area of d times your height. And in this case, our height is just 1. So this would be area of d times 1. And this gives us our volume. So even though our final answer, when f of xy equals 1, is area of D, this is not measuring area. It's giving you the volume. So this is a measurement of volume, but this is our numerical answer. It would be the same as if you were to take the area. Okay? All right, moving on to the next topic on the next slide. Now we're going to be exploring something called an iterated integral. So iterated, that's a funny word. Iterated integrals. So what this means is that iterated, whenever you see that, that just means can be evaluated in steps. Okay, so you're going to do one thing and then another thing and maybe even another thing. So let's look at an example. We have the double integral, and here are our bounds. We have f of x comma y, and this time dy comes before dx. Okay, so let's figure out the intervals here. So on the outside we have dx corresponding to a and b, so that means that x is between a and b. All right, and then on the inside we have dy corresponding to c and d, so that means y is going to stay between c and d. Okay, so we have that so far. And then the way that you would evaluate these is the following. So what I do is I rewrite it, okay, and then I put parentheses around the inner ones. So parentheses here and parentheses here. So the dx stuff is staying outside, basically, okay? So what this means is we're going to be, in this first step, right? So the first step is to look at the y stuff on the inside, or whatever is inside, because sometimes you could have the x stuff inside first. But anyways, so what you do here to evaluate this part, everything in parentheses, is the following. So you're going to treat any x's that you see, like this x, as a constant. So remember I said constants, they are not variables, because they stay constant. And you can treat it just like another number or something. So you're going to treat x as a constant, and then you evaluate the inside. Evaluate. Woo, can't spell. Evaluate inside integral. Okay. With your given y interval. So this is ranging from y equals c to y equals d. So with y interval. Ooh, sorry, I got a little messy back there. Okay, and then, so this is like your first step. And then your second step would be, I'm just going to write it out here, and then we'll do an example. And then you're going to take whatever you get. So now we have a of b, and then inside, we're actually going to get some function of x, okay? Because, well, you'll see on the next example, as I said, but when you're evaluating the inside integral, everything having to do with y's, when you plug in the y values, it'll turn out to eliminate all of the y's in it. So then you'll be left with some function of x alone. Okay, so then that transforms into this, and you're left. This is just a single variable integral, right? Like we've seen in high school calculus kind of thing. Yeah, and then you just evaluate the single integral left over. Okay, so as I said, we can start an example on the next slide. So here's our problem. Integral from 1 to 2, and then integral from 3 to 4 of xy, dy, dx. Okay, so the first step, like I said, what I like to do is write parentheses around the inner one, so I know what I'm going to focus on first. Okay, so ignoring everything outside of the parentheses, let's just look at this. So the first step, since we're integrating with respect to dy, is to treat all x's as constants. So x is like a constant, okay? So remember what that means is whenever you have a constant, you can bring it outside of the integral, right in front. So I'll do that on the next step. So I'm going to bring x outside, and then we have from 3 to 4 of y dy, close parentheses, and then the dx is just floating outside there. Okay, so now let's just evaluate like normal. So we have, and you just have to keep rewriting everything on the outside that we don't really, that we aren't really concerned with right now. But then we have 1/2 y squared evaluated from y equals 3 to y equals 4. Okay, and at this point I'm just integrating like normal, and then dx. Okay, and this x over 2, we can actually just bring this outside, but I'll just keep the constants inside for now, so it's not confusing. So x is here, and then we have, if I plug in the 4, then I get 1/2 times 4 squared minus 1/2 times 3 squared. Okay, and dx. Right, and we'll just keep going here, simplifying. 1 to 2, x, and this is a 16 over 2 minus 9 over 2, which is a 7 over 2, if I'm correct. Okay, and then we have our dx. All right, so as you can see, everything inside parentheses, we've eliminated the y's, right, because we plugged in actual values for the y. So this is like our g of x that I was talking about in the last slide. So just some function of x, okay. So now that we're integrating, that now that we are integrating with respect to x, we can consider x as a variable, okay. So now x is variable. Okay, and 7 over 2 is always going to be a constant no matter what variable you are integrating with respect to, so I'm going to bring that outside. So we have 7 over 2 from 1 to 2 x dx. Okay, and then we'll keep integrating here, so 7 over 2 times 1/2 x squared, and now x is going from 1 to 2, and then we just plug in things. I'm going to combine the coefficients here, and then we have 2 squared minus 1 squared, which is going to be 7 over 4 times 4 minus 1, which is 3. So our final answer is 21 over 4. All right, and this gives you, this is a positive value, so this is a positive volume. Okay? Alrighty then. So now, all right, we're going to go on to another pretty important theorem.
Honey's feeling deep in their placenta, cold as the pole in the winter. Far from the inventor, but I got this rap shit sold, and when my Mac loads, I'm guaranteed another video.